This is 2.5 review, and this is number 1. So we have this equation, 2N2O5. Is it coming up there yet? Not yet. It will. Oh, it's a little slow today. I'm just going to write it down. 2N2O4, there it is. 2N2O4 plus O2. And these are all gases, so I'm going to leave the gases out for right now. I think it's a little slow because I didn't update my reflector driver. All right, so it gives us that the forward reaction, right, the R forward is going to equal 2.7 times 10 to the minus 3 times the concentration of N2O5 squared. And it also gives us that the rate in the reverse is equal to 4.3 times 10 to the minus 2. And that's going to be N2O4 squared times O2. Now, how do you know that they're squared? I mean, I know these are given, but for equilibrium, what do we know about the forward rate and the backward rate? They're equal, right? So in equilibrium, the forward rate, these two have to be equal, so let's set them equal. So we're going to say 2.7 times 10 to the minus 3 times N2O5 raised to the 2 is going to equal 4.3 times 10 to the minus 2 times N2O4 squared times O2, concentrations, right? And we want to derive the equilibrium constant is what this asks, derive K equilibrium. So the equilibrium constant, it has to be the products, the concentration of the products raised to their powers over the concentration of the reactant. So we're going to take this equation and we're going to divide both sides by the reactant to get the products over the reactants. Right? And so now this cancels out. And then if we divide both sides by the rate constant, that's in the reverse direction, we get the expression for the equilibrium. We get that this number here is going to equal the rate or the concentration of N2O4 squared times the concentration of O2 over the concentration of N2O5 squared. And that is the equilibrium constant. So what we just did is we found that this number is the equilibrium constant using the rates. So go ahead and do that division. Let's see what we get. Okay, and you don't need any units on equilibrium constant. Isn't that nice? Because they get complicated and they're not super important in this part of the class. Okay, so this is the answer. The equilibrium constant is 0.063. Okay, so that's the equilibrium expression for 3A, and you can do the rest of those. Okay, let's jump to number 8. So number 8, it says, write the equilibrium expression for each of the following, and I'm going to emphasize this, so I'm going to write the problem. Iron solid plus 2H plus aqueous is in equilibrium with H2 gas plus Fe2 plus, okay, iron 2 aqueous. Equilibrium expression, products over reactants, but does not include solids and liquids. Products over reactants does not include solids and liquids. Let's put the products over reactants. So H2 gas times Fe2 plus aqueous divided by, do I put Fe on the bottom? No, it's a solid. Don't put Fe on the bottom. Divided by H plus raised to the what? 2. Okay, so I haven't actually recorded on this, so while you do the calculations, I'm going to just walk back through what this screen says. So we're taking the example on page 154. Go ahead, you guys do the number crunching that we're at. And we took a look at the equation on page 154 and how the K equilibrium was 9. And the question was, well, what if we multiply a reaction by 3? Will we raise the K equilibrium to the power of, will you raise it to the third power? Because if you double a reaction, you square the K. So we multiplied that by 3, and we got 6H2O plus 3O2 is in equilibrium with 6H2O. 6H2 plus 3O2, equilibrium with 6H2O. We're going to take the same concentrations because we know that those are in equilibrium, which might not be intuitive, but I'm going to tell you that that's the case. Okay, and we're going to plug in our numbers. Okay, so we got some big numbers, 12 raised to the 6th. Okay, so this comes out to be 729. Well, guess what? What's 9 times 9 times 9?
7.
So
you cube that number every single time?
So whatever you multiply, so what we just did is we took a reaction and we multiplied the coefficients of that reaction by number. That's how we got these coefficients. When you multiply a reaction, the coefficients in the reaction by a number, because you know how sometimes the coefficients are a half when we're doing certain types of problems, and we don't like halves in most of our balanced equations. So a lot of times you have to double a reaction. If you multiply a reaction by number, the K equilibrium gets raised to that power for the new reaction. It's a power law as opposed to a multiply law for the K. Okay, so that's going to help us when we go to do the problems that we were just on. Now, if we reverse a reaction, what was the rule for the K? So K equilibrium of the reverse reaction equals what? 1 over K equilibrium of the forward reaction. Okay, so those are two different numbers. The K reverse, and a lot of times this might be called K prime. This one might be a K prime. Prime just means a new K, okay? But the K reverse is 1 over the K forward. So now let's take a look at the problems that we were working on. All right, so number 10 says, for each of the following, what is the K equilibrium at 462? What's super important there? Why do they tell us the temperature? 462. We're given 2 NOCl gas is in equilibrium with 2 NO gas plus Cl2 gas. And it says that the K equilibrium for this is equal to 8.0 times 10 to the minus 2 if we're at 462 degrees Celsius. And then all of the questions say at 462 degrees Celsius because K is dependent on T. You can't do these things if you change the temperature. If you change the temperature, the K, you can't do these calculations. The K changes. Bye. Okay, so the first one, what did we do the first one? So for 10A, the new reaction that it's asking us is, what if the reaction was this? So the question is, what did we do to this reaction to get that reaction? We halved it. So we're going to take the K equilibrium and we're going to raise it to that power because we did 1/2 times that, so we have to raise it to the 1/2. What's the 1/2 power the same as? The square root. So this means that it's the square root of the original K. So what do you get? Square root of 8 times 10 to the minus 2? 0.283. Okay, now let's look at B. B says we have 2NO gas plus Cl2 gas is in equilibrium with 2NOCl. What did we do to the original reaction to get to there? We reversed it, okay? So if we reversed it, the K of this is going to be 1 over the K forward. So 1 over 8 times 10 to the minus 2. So what do you get for the K reverse?